Earth has existed for billions of years. So what makes us believe that we are the first civilization on this planet? But what if that belief is not entirely true? What if, before our first cities were ever built, Earth had already witnessed other ages? Then how did whatever existed before us disappear? Geology does not lie, but it does not tell the whole story either. It preserves only what is durable enough to survive millions of years. And within that silence, a question begins to take shape slowly, yet insistently. Are we walking on a young planet, or on the sleeping remains of histories far deeper than human memory? And now, take a slow breath and allow your thoughts to settle. Tonight, let us drift together into a journey through deep time, where science does not rush toward answers, but opens the door to possibilities that have long been asleep within this planet. As the world around you grows quieter, we begin our journey gently exploring what the Earth may still remember beneath its ancient layers. Beneath our feet, far below soil, roots, and familiar stone, the Earth keeps a quiet memory, layer by layer. It has recorded moments of calm and moments of upheaval, each pressed gently into rock over spans of time so long that they soften the meaning of years. In one of these deep layers, formed around 65 million years ago, something unusual rests, something small, subtle, and easily overlooked. Scattered through this ancient rock are tiny metallic spheres. They are microscopically small, almost like grains of dust frozen in stone, and they appear not in one place, but across the planet. They are rare metals, shaped into smooth, rounded forms, as if once melted and sprayed through the air before settling slowly onto the ground. Their distribution is calm and even, global rather than local, quiet rather than dramatic. When modern scientists first studied them, their pattern felt strangely familiar. Similar microscopic spheres are produced today by intense industrial processes, by extreme heat, rapid cooling, and energetic reactions. In our own time, such particles can appear after powerful technological events, including those involving nuclear reactions. And yet these ancient spheres formed long before any human hand, long before cities, engines, or even mammals like us walked the earth. They sit there quietly, these metallic dots in stone, not announcing anything, not demanding interpretation. They simply exist, like industrial dust gently pressed into geological memory. Their presence does not insist on a story, but it opens a space where imagination and observation can drift together, calmly, without urgency. From this small and delicate detail, our journey widens. Just above that same span of time in the rocks, there lies another layer, thin, almost fragile, yet unmistakable. It is a narrow band of clay, found in many places across the world, marking a boundary between two vast chapters of life on Earth. Within this clay, scientists discovered something rare: iridium. Iridium is an element that Earth's surface rarely holds in abundance. It prefers the depths of planets, not their crusts, but it is common in objects that wander through space. Asteroids, formed far from Earth, often carry it in generous amounts. And here it was, concentrated in this thin global layer, far richer than anything normally found in surface rock. This quiet line of clay tells a story without words. It speaks of a single day, unimaginably long ago, when something from space arrived, an asteroid, vast beyond human scale, met the Earth near what is now the Yucatan Peninsula. In that instant, energy beyond description was released, and the planet changed course. Dust rose, climates shifted, and the age of the dinosaurs, gently, but irrevocably, came to an end. What is remarkable is not only the event itself, but the clarity of its signature. Tens of millions of years later, the Earth still remembers. A thin line, a trace of iridium, a quiet, readable mark in stone. And so, without haste, a gentle idea forms. If a single day of cosmic violence can leave such a clear geological signature, then any event that reshapes atmosphere, chemistry, or energy flows may also leave a mark. The rocks do not judge the source. They simply record. From this understanding, some scientists have allowed their thoughts to drift a little further. They have asked, calmly and carefully, how we might recognize the traces of an industrial civilization, not our own, but one that might have existed long before us. This line of thinking has come to be known as the Silurian hypothesis. It does not rush toward conclusions. It does not claim that such a civilization existed. Instead, it rests in a quieter space. It wonders what kind of signatures industry leaves behind, and whether, over vast spans of time, those signatures might blend softly into natural processes, becoming difficult to distinguish. In the immense story of Earth, human industry occupies only a thin sliver, a few thousand years, set against billions. On the scale of geological time, this is barely a breath. If Earth's history were a library of millions of books, the entire industrial age would fill perhaps a single page, slim, delicate, and easy to miss. Stone erodes, mountains soften, oceans recycle their floors, cities crumble into dust long before rock layers settle. It is natural, then, that machines, roads, and structures would fade almost completely. What remains, if anything remains at all, would not be monuments, but whispers, subtle chemical shifts, faint isotopic changes, traces pressed quietly into sediments. This realization gently shifts our attention. Instead of searching for ruins, we begin to notice patterns, changes in atmospheric gases, captured in ice or stone, unusual concentrations of metals, materials that resist decay more stubbornly than bone or wood. In our own time, we are leaving such marks without ceremony. Carbon dioxide spreads through the air. Plastics drift into oceans and sink into mud. Artificial isotopes settle into soils and sediments. Waiting patiently, all of this is being written, calmly and continuously, into the geological record. And so, by observing ourselves, we gain a lens for the past. Not a lens of certainty, but of possibility. The rocks may hold stories that do not announce their authors. They may record episodes of energy use, of atmospheric change, of industrial intensity, without preserving faces, names, or cities. In this quiet perspective, the Earth feels less like a puzzle to solve and more like a long, slow archive. Some pages are clear, others are smudged, many are missing entirely. And that is all right. Here, at the edge of deep time, we do not need answers. We simply rest with the idea that the planet remembers more than we often assume, and that memory, like sleep itself, does not reveal everything at once. It unfolds slowly, gently, layer by layer. As we continue drifting onward through the calm vastness of time, the fossil record is a buried book, pressed into stone and weathered by the arrival and departure of ancient oceans. When we examine this record, we do not find a tidy, linear narrative from the first cell to the present. Instead, we find scattered chapters, sentences beginning mid-thought, and vast stretches where the pages are missing entirely. What remains is a partial memory of a planet that has been alive for an unthinkably long duration. In this book of stone, certain creatures appear with startling clarity, those with hard shells or sturdy bones. Others, especially soft-bodied or delicate forms, slip through the net of preservation. Entire ecosystems may have flourished and vanished without leaving a trace. Consequently, our knowledge of evolution is not a complete panorama, but an arrangement of fragments. We must walk carefully among these relics, aware that between any two fossils may lie vast ages of unrecorded change. Within these missing pages, many possibilities rest. There may have been stages of biological organization or periods of complexity that do not appear in the strata we have examined. Some speculate about phases of activity that might even appear industrial to us, rising and fading before the studied layers were ever laid down. Regardless of whether such ideas are true, we must recognize that the geological record does not claim to be exhaustive. The silence between its words can hold multiple interpretations. As we move along the timeline, the record suddenly grows dense and vivid. Approximately 500 million years ago, the strata reveal a rapid flourishing of marine life known as the Cambrian explosion. Before this interval, the world was dominated by simpler, understated organisms. After it, the oceans teemed with creatures possessing eyes, shells, articulated limbs, and intricate body plans. In the rocks, this transition feels less like a gentle hill and more like a cliff. Many lineages appear fully equipped with complex structures, leaving only disputed hints of their gradual evolution. While biology offers mechanisms to explain this new ecological interactions, chemical shifts, or genetic innovations, the sense of a jump remains. Life seems to have shifted gear, moving from subtle to spectacular in a span that is strikingly rapid in the language of deep time. Some view this as the combined effect of evolution and imperfect preservation. Others wonder if such episodes represent broader cycles of planetary reorganization. Further back in time, we encounter a transformation not of shape, but of chemistry. More than 2 billion years ago, photosynthetic microbes began releasing oxygen as a metabolic byproduct. Initially, this oxygen was absorbed by rocks and oceans, but eventually, the balance shifted. Free oxygen began to accumulate in the atmosphere. The Great Oxygenation Event was a profound chemical rewriting of Earth's surface. For microbes that thrived in anaerobic oxygen-free environments, the change was catastrophic, narrowing their habitats. For future life, it opened pathways for complex metabolism and new tissues. The rocks preserve this upheaval as changes in mineral composition, quiet evidence that the planet's outer layers were altered on a global scale by the simplest of life forms. This event offers a template for how living systems reshape a world. Without intention or technology, simple cells altered the chemistry of the sky so deeply that the effects are visible billions of years later. It follows that any advanced civilization working with energy and materials on a planetary scale would also leave marks. To a future observer, those marks might appear as a natural shift unless they knew exactly what to look for. This pattern of appearance and disappearance continues through the ages. Groups emerge, diversify, and decline. Ecosystems reorganize around what survives climate shifts, tectonic movements, and asteroid impacts. Because the conditions for fossilization are uneven, some eras are documented in rich detail while others are softly veiled. These factors create an impression of steps in evolution rather than a smooth slope. Scientific explanations for these gaps are well grounded. Soft tissues rarely fossilize. Many environments are poor at preserving remains, and tectonic activity erases entire rock sequences. These are not weaknesses in science, but part of the honesty with which we must approach the past. Many missing stretches coincide with moments of intense change in climate or atmospheric composition. Noticing this alignment does not require us to abandon established reasoning. It simply invites a widening of the lens. The incomplete fossil record is not a problem to be solved, but a landscape to be navigated with humility. The torn pages and sudden leaps suggest that Earth's story is both knowable and mysterious. We hold the fragments time has allowed us to keep, leaving the missing portions open, like quiet rooms, in a vast library where histories rested before fading into stone. On a planet with a deep and restless history, industry does not always leave behind visible ruins or shining machines. Its memory can be much quieter, written into chemistry, trapped in bubbles of ancient air, or hidden in grains of dust that settle layer by layer, long after buildings have fallen and metals have corroded away. The most persistent traces can be subtle patterns in carbon, unusual particles in sediments, and synthetic materials that behave more like minerals than tools. When we look at Earth through this lens, we begin to read a different kind of archive, one that carries the shadows of energy and transformation across enormous spans of time, far back in the past, around the boundary between the Permian and Triassic periods. Life on Earth passed through an immense crisis. A large share of species disappeared, and ecosystems that had been stable for ages gave way to unfamiliar forms. In the rocks that record this turning, the balance of carbon isotopes shifts abruptly, as though a huge reservoir of old carbon was suddenly released into the air and oceans. The pattern is reminiscent of what happens when large quantities of fossil carbon are burned or rapidly oxidized, sending lighter carbon into circulation faster than natural processes usually allow. There are calm explanations rooted in geology and climate for such a signal. Vast volcanic regions could have poured out gases for long intervals, warming the climate and disturbing the carbon cycle. Warming seas might have released methane that had been stored in icy structures on the seafloor. Forests and peatlands could have burned on continental scales, turning buried organic matter back into gas. Each of these processes can create the kind of isotopic jump we see at this ancient boundary. And together, they form a natural picture of a world in upheaval. What makes this pattern quietly thought-provoking is its similarity, in outline, to the mark that human activity is now imprinting on the atmosphere. Today, our use of fossil fuels is changing the same isotopic ratios, though on a smaller absolute scale and over a much shorter time. The resemblance suggests a gentle idea. The rocks tell us that a large, rapid release of stored carbon occurred, but not whether the hands behind it were volcanic, biological, or technological. From the standpoint of chemistry alone, different stories can produce similar signatures. That uncertainty does not trouble the rocks. It simply reminds us that they record what happened more clearly than who caused it. Tang. This is bring so every genus much nearer to our own present. In terms of deep time, ice cores, taken from Antarctica and Greenland, preserve a detailed diary of the air over hundreds of thousands of years. Thin layers of snow compact into ice, trapping tiny bubbles that hold the composition of past atmospheres with remarkable fidelity. Within these frozen columns, levels of carbon dioxide and methane rise and fall with the slow rhythm of glacial cycles, responding to subtle changes in Earth's orbit and the reflective power of ice and clouds. Amid these broad swings, there are sharper peaks, where greenhouse gases climb more quickly and remain elevated for a few thousand years before sliding back toward earlier values. Climate science describes these features using well-established ideas: feedbacks between ice cover and temperature, changes in ocean circulation, shifts in vegetation, and the delicate pacing imposed by orbital variations. In that framework, the peaks take their place as parts of a complex but natural climate machine, one that breathes in and out over long periods. Seen from another angle, as we let our thoughts drift gently, those same peaks resemble brief phases where the planet's energy balance is pushed a little harder than usual for a relatively short span. The shape of the curve could, in principle, match what an industrial phase might look like when measured in ice layers rather than calendar years. The same pattern can arise from different causes, and the ice itself does not insist on a single interpretation. This soft ambiguity shows how a short-lived, energy-intensive period could blend into natural variability, leaving a signal that is noticeable yet not easily separated from other influences. Beyond gases and isotopes, there are traces left by high temperatures and fine dust. When material is melted and sprayed through air, then cooled quickly, it can form tiny spherical particles. Modern industry creates such microspheres in power plants, smelters, and other facilities that heat matter intensely. These particles float through the atmosphere and settle into soils, riverbeds, and the floors of lakes and seas, forming a faint but widespread sprinkling of industrial ash. Ancient rocks and sediments also contain spherical grains of glass and metal, produced by natural processes such as volcanic eruptions, lightning, and the fiery passage of cosmic dust through the atmosphere. Some are enriched in particular elements. Some are concentrated in thin layers associated with impacts or major eruptions, and some are more widely dispersed. Under a microscope, the resemblance between natural and industrial spheres can be striking. Shape and size may be similar, and even the chemical makeup can overlap in certain ranges. This similarity suggests a quiet lesson about how the planet records high-temperature events. Whether the source is a factory chimney, a volcano, or incoming cosmic material, the end result can be tiny, rounded grains scattered through sediments. To distinguish among these origins, one must look for patterns in distribution, in companion minerals, and in the context of surrounding layers. If another civilization had once filled its skies with metallic dust, its particles might mingle with volcanic ash and spaceborne spheres, becoming part of a mixed background that would demand great care to interpret. The grains would still be there, but their story would not announce itself. Modern human activity has introduced another class of persistent markers: synthetic polymers. Plastics, designed from long chains of carefully arranged molecules, resist breakdown and spread easily through air and water. In recent decades, microscopic fragments of plastic have begun appearing in river sediments, coastal sands, and the deep ocean floor. They mix with natural particles, forming hybrid layers where organic matter, minerals, and manufactured polymers lie side by side. Because of their durability and worldwide distribution, these fragments have been proposed as potential indicators of our current era in the geological record. If any earlier culture had created its own version of durable synthetic materials and released them widely, small pieces might also have found their way into sediments, where they could persist as tiny inclusions long after other artifacts had vanished. In practice, when unusual particles are discovered in older layers, careful work usually traces them to natural mineral structures, biological remains, or modern contamination. The principle remains. However, sturdy, artificial compounds have an unusually good chance of surviving as dust and grit, even when the larger objects they once formed have disappeared. Alongside polymers, present-day technology relies on advanced composites and alloys, crafted to endure heat, pressure, and corrosion far beyond what ordinary materials can tolerate. Designed at the level of crystal lattices and molecular arrangements, they might one day behave, in the eyes of distant geologists, more like a strange kind of rock than a piece of machinery. Over millions of years, bridges, vehicles, and devices would fall apart. But the toughest fragments could remain embedded in sediments, transformed into odd, localized clusters of unusually arranged matter taken together. These examples reshape how we imagine the lasting footprint of a technological age. The most enduring legacy may not be towering buildings or complex devices, but gentle shifts in isotope ratios, repeated patterns in greenhouse gases, thin layers of high-temperature dust, and scattered grains of synthetic material. When we look at Earth's stone, ice, and mud with this in mind, we see not just the history of life, but also the quiet possibility that energy-using civilizations write their presence into the planet in ways that are easy to overlook, yet difficult to erase, resting patiently within the slow, deep layers beneath our feet. Nuclear processes leave traces that outlive the devices, societies, and landscapes that first set them in motion on a restless planet. Their signatures settle into minerals, glide into crystals, and rest inside layers of rock that endure through vast, silent ages, long after reactors cool and weapons, if any existed, have vanished. Patterns in certain isotopes remain as a quiet memory. In the early 1970s, geologists studying a uranium deposit in Gabon noticed something unusually gentle yet unmistakable in the ore. The proportion of one uranium isotope was lower than it should have been, as though it had already fueled a chain reaction. Detailed measurements showed that, about 2 billion years ago, conditions there allowed a natural nuclear reactor to operate. Groundwater slowed neutrons. The geometry of the deposit cooperated, and the system turned itself on and off for a very long time. What stays with us is not only the idea of a natural reactor, but the clarity of its surviving trace. After such an immense stretch of time, the rocks still carry daughter products in patterns that reveal what once occurred. Some isotopes are enriched, others depleted, together forming a distinctive nuclear fingerprint that differs from ordinary ore. Oklo shows that when countless nuclei are rearranged, their history can persist across almost inconceivable ages. From this example, thoughts drift gently toward reactors that are not purely natural. If a self-sustaining chain reaction leaves such a clear imprint, then any artificial reactor should also mark its surroundings. The same physics would govern a simple power plant or a design of breathtaking sophistication. In this sense, a planet becomes a patient archivist, keeping the outcomes of nuclear work in the fine accounting of isotopes. In our imagination, we picture other uranium deposits resting in ancient crust, far removed from human industry. In some, the isotope ratios resemble those produced by steady power reactors, shaped by long, controlled operation. In others, the pattern appears more abrupt and uneven. Closer to what follows, repeated tests of compact, concentrated devices. The rocks holding these ores would be many tens of millions of years old, laid down long before our species arrived. These imagined deposits invite a soft comparison between different kinds of nuclear behavior. Natural reactors, like the one at Oklo, are constrained by geology, groundwater, and the tendency of systems to balance themselves. Their activity changes slowly and remains relatively moderate, even over long spans. Weapons testing concentrates energy into short pulses, leaving sharper, jagged signatures in nearby materials. If old ore bodies carried patterns closer to the latter, they might quietly suggest actions more deliberate than geology alone. Beyond solid rock, the planet keeps archives in ice and in slowly settling mud. Snow that fell long ago still lies compressed within polar ice sheets, holding bubbles of ancient air and traces of fine particles. On the ocean floor, sediments accumulate grain by grain, recording what rivers delivered and what drifted down through the water column. Together, these layered records already reveal the global reach of recent nuclear activity, preserved as fallout in ice and seafloor mud. And attention lingers for a moment on older sections of these frozen and muddy archives. In some layers that align with past intervals of ecological stress, we picture faint enrichments in radionuclides that rarely occur naturally. Certain isotopes resemble those produced in reactors, others those born in high-energy experimental machines. Their half-lives allow them to persist for many thousands of years, serving as ink that fades slowly rather than disappearing. Any true search for such signals would need great caution, because contamination and natural background processes can easily confuse the picture. Yet the principle itself remains simple and steady. If a civilization were to harness nuclear energies on a planetary scale, its radiological echoes would be hard to conceal completely. Even if cities fell and metals rusted away, some isotopes would linger in ice, clay, and carbonate minerals, gently. The scenario expands from scattered traces to truly large scales. Certain rock layers might show concentrations of radioactive elements higher than any known natural background. When modelers tested simple explanations, they might find that thousands of explosions, or an equivalent release of nuclear energy, would be required. Mixed among familiar fission products, hints of stranger isotopes could appear, ones that seem to demand techniques beyond current engineering. In this picture, those layers become quiet witnesses to times when nuclear forces were shaped for more than gentle power. Planets touched by such activity would not remain visibly scarred forever. Yet their crusts would carry the memory in ratios and decay chains. The details of those periods would vanish. Yet the outline would remain, a burst of nuclear change, then long cooling. Seen in this tranquil light, the lasting trace of an advanced age may not be monumental structures or enduring texts. Instead, it may be subtle shifts in elemental balances and uncommon isotopes that sleep deep underground. Oklo reminds us that even natural reactors can leave signatures that persist across nearly half the planet's history. Layered upon that example, our quiet speculation suggests that any deliberate nuclear age would also be written into stone, ice, and sediment. Long after memories and stories have faded, a patient world would still carry those marks within its ancient strata. Beyond the brief, intense flashes of nuclear change, another kind of intervention appears, quieter and slower, the deliberate reshaping of climate. On a living world like Earth, climate is not only weather passing overhead, but a long, slow pattern written into air. It changes with continents and oceans, with the tilt of the axis, with ice advancing and retreating, yet it also remembers, within that memory, held in ice, rock, and sediment. Patterns sometimes appear that resemble the breath of industry itself. Deep in Antarctic ice and the glaciers of Greenland, tiny bubbles preserve the composition of ancient atmospheres with remarkable faithfulness. Across hundreds of thousands of years, levels of carbon dioxide and methane rise and fall in step with glacial cycles and orbital rhythms. Among these broad swings, there are episodes where greenhouse gases increase rapidly, reach unusually high plateaus, then slowly relax toward earlier values, seen as lines on a graph. They echo the shape of our own age, a sharp climb driven by energy use, followed by a long, gentle settling. In our imagination, these pulses become the quiet breathing of civilizations that once learned to tap deep stores of carbon for power. For a while, their engines might have filled the air with additional greenhouse gases, warming their world and driving their technologies. Later, their emissions may have faded as they changed energy sources or as their cultures declined, leaving the climate to inch back toward balance. When such pulses repeat over long stretches of time, they hint softly that civilization may be a recurring pattern rather than a single event. The atmosphere, however, holds more than just the record of gases. Tiny particles drift through it, reflecting sunlight, seeding clouds, and eventually falling into seas where they settle into slow blankets of sediment. In some imagined layers, chemical traces appear that look very much like the aerosols and engineered compounds our own species has proposed for climate control. These substances would scatter incoming light or alter the behavior of clouds, gently adjusting how much warmth a planet absorbs from its star. If such materials appeared precisely when climate stayed unusually stable, despite natural forces pushing it toward change, they would invite a thoughtful reading. Instead of a planet simply obeying its orbital cycles and volcanic moods, we would be seeing a system carefully guided within narrow limits. The sediments would resemble a subtle control panel, where concentrations of reflective particles and radiative agents rise and fall like dials once turned. In that picture, industry matures into climate engineering, and a civilization learns not just to endure weather, but to shape it. Beyond aerosols and greenhouse gases, The very proportions of the main atmospheric gases might also carry signs of deliberate adjustment. Samples of ancient air, preserved in deep ice or trapped within amber, sometimes show oxygen at levels higher than modern values. In an imaginative scenario, certain isotopic ratios could hint that this oxygen had been enriched in ways that look more like industry than biology. Nitrogen, too, might bear patterns suggesting it had been processed and redistributed to favor combustion, materials production, or the protection of delicate structures from corrosion. Such a world would feel almost like a planetary laboratory, where the atmosphere had been tuned to serve the needs of advanced technology. Ratios of oxygen and nitrogen would still support life, yet they might also be arranged to optimize engines, reactors, or exotic chemical processes. Here, the step is no longer simply using climate, but quietly redesigning the sky itself, turning the air into a vast, invisible tool. The boundary between environment and infrastructure would blur. As the medium every creature breathes becomes part of a deliberate industrial system, not every attempt to adjust a planet's air would succeed. In the geological record, we might see rapid compositional shifts, followed by quick reversals, as though certain atmospheric states had been tested, then abandoned. Greenhouse gases could surge, unusual aerosols could appear, and other reactive compounds might rise briefly, only to retreat when their side effects proved too strong. Each of these episodes would resemble a trial version of a new climate, a configuration briefly installed and then gently rolled back. This vision carries a quiet reflection. Even a culture with immense knowledge could misjudge the complexity of a living atmosphere and the webs of response it contains. Attempts to stabilize conditions might instead trigger cascades of feedbacks, touching oceans, ice, and ecosystems in ways nobody planned. The record of such experiments, if they ever occurred, would rest in thin, chemically distinct layers that whisper of both ambition and caution. There is also room in this story for atmospheres that were never meant for beings like us. Some ancient gas mixtures may have been rich in compounds that our lungs would find hostile, yet perfect for a very different kind of biology. A civilization built on alternative chemistry might thrive in an air that seems toxic by human standards, drawing energy and structure from gases we avoid. For such life, an atmosphere shaped to their needs would be as gentle and supportive as our own is to us. When we imagine these possibilities, the current human pattern becomes only one verse in a longer atmospheric song. Multiple rounds of copying, testing, and discarding different sky designs could have unfolded, each linked to forms of life that no longer exist. Our present balance of nitrogen, oxygen, and trace gases might be just one more arrangement in a sequence of carefully tuned environments. The air around us then feels less like a background and more like a quiet, living archive, holding the memory of experiments in climate and habitability that span deep time. On a world as old as Earth, an extinction is not only an ending, but also a quiet reshaping of what can live. Over deep time, life has bloomed, faltered, and bloomed again, as though the planet sometimes prunes its own garden. The great die-offs that mark the geological record become turning points, where one version of the biosphere fades and another begins to unfold. Among these, the vast crisis at the boundary between the Permian and Triassic periods stands out with a particular stillness. Almost all known marine species disappear from the record, and many land dwellers vanish as well, leaving empty ecological space. Yet, when scientists examine which groups survive and which are lost, the pattern does not look entirely like random damage. Some creatures that seem fragile manage to continue, while others that appeared well adapted to their environments fall away. This selective pattern can be read very calmly as the outcome of complex environmental stresses. Different physiologies and lifestyles respond in different ways to heat, lack of oxygen, or changing chemistry, and some simply cope better, Still, the arrangement has a strangely focused character, as if certain branches of the evolutionary tree had been thinned with particular care. From this example, thoughts can drift toward a gentler, speculative picture, where extinction is not only chaos, but also a possible tool. In that picture, a civilization deeply familiar with biology might one day learn to influence which lineages endure and which quietly end. Instead of striking every organism equally, it could design pressures that touch certain metabolisms, tissues, or reproductive strategies more strongly. The result would resemble a vast, planetary filter, removing some evolutionary pathways while leaving others free to expand into cleared space. The Permian-Triassic crisis becomes, in this soft vision, less like a single blow and more like a difficult, directed adjustment of the biosphere. If living systems can be guided in this way, invisible agents would almost certainly play a central role. At the boundaries of several extinctions, rocks and sediments could, in such a scenario, hold traces of unusual toxins or engineered microbes, molecular structures not known from ordinary chemistry, and genetic patterns that hint at deliberate modification would be the quiet remnants of their work. These signatures would not show the conflict itself, only the tools that once moved through oceans and soils, shaping outcomes at the smallest scales. It is possible to imagine a hidden struggle unfolding across an ancient Earth, almost entirely beyond direct perception. Tiny organisms drift through water, ride air currents, or spread through root systems, nudging some species toward collapse while leaving others untouched. To the animals and plants experiencing it, the change would feel like sickness, scarcity, and altered conditions, not like war in any familiar sense. Yet to a distant reader of the rocks, certain layers would carry consistent traces of synthetic poisons and unusual genomes, hinting at purposeful design. Placed alongside nuclear and climate interventions, such biological tools would complete a quiet set of planetary instruments. Some technologies would heat or cool the world. Some would alter its chemistry. And some would work directly on the fabric of living communities. Together, they would turn mass extinction from an unpredictable disaster into something more like a controlled, if perilous, procedure. Farther back, another great die-off marks the boundary between the Ordovician and Silurian periods, when many marine species disappear from the seas. Afterward, new groups rise and spread, filling ecological spaces that had been emptied only a short geological moment before. Some of these newcomers seem almost pre-adapted to the cooler waters and shifting coastlines that follow the extinction. They settle quickly into roles that fit the new conditions with surprising ease, as though they had long been waiting behind the scenes. This pattern can be seen as evolution working very efficiently, exploring possibilities until it finds solutions that fit the changed world. It can also be viewed, just as gently, as if older communities were being retired to make way for successors already prepared. The stage clears, and another caste steps forward, able to thrive in waters that would have challenged those who came before. In that sense, the extinction acts less like a random storm and more like a difficult but carefully timed change of scene. Later still, at the end of the Cretaceous, the trace of a very different kind of event lies in rock and crater. An object from space strikes what is now the Yucatan region, releasing an enormous amount of energy and disturbing climate and ecosystems worldwide. A thin layer rich in certain elements, along with shocked minerals and glassy droplets, records the passage of this visitor from beyond. In the wake of the impact, many large reptiles, including the non-avian dinosaurs, disappear, and new groups of mammals slowly begin to rise. The usual story describes an asteroid wandering along its orbit until chance brings it into collision with Earth. Alongside that, another quiet possibility can be held without insistence. A civilization with deep knowledge of orbital mechanics might, in principle, learn to nudge such bodies over long timescales. Small changes in speed or position, accumulated patiently, could one day steer a rock onto a path that intersects a chosen world. From this example, the impact becomes, in imagination, less a random stone and more a shaped instrument, wielded with immense caution. Directed in this way, a single object could bring an age to a close and open ecological room for a very different one. To the planet, the physical damage and subsequent recovery would unfold much as before. To the pattern of life, however, the shift might reflect not only natural celestial dynamics, but also a distant choice. When these images are set side by side, mass extinctions begin to look like the most powerful adjustments a planet can experience. Nuclear events, climate engineering, biological tools, and guided impacts form a spectrum of influence reaching from the microscopic to the cosmic. Each can, in principle, reshape who lives, who fades, and which forms of organization have space to unfold. The biosphere becomes a patient, resilient system that sometimes passes through narrow gates before expanding into new and untried shapes. However, we understand these ancient crises. The pattern they leave behind is one of loss followed by renewal, absence followed by quiet abundance. For long stretches, life seems stable. Then a sudden contraction arrives, and afterward, different creatures inherit the oceans and the land. In that slow rhythm, extinctions act like deep breaths drawn by the planet itself, rare and heavy, yet followed by long exhalations of new diversity. Drifting along this timeline, we can simply notice how often endings and beginnings lie close together, sharing the same thin layers of stone. At the very bottom of the world, beneath winds that circle endlessly and snows that rarely melt, lies a continent almost entirely hidden from view. Most of what we know about Antarctica comes from its surface ice and the cores drawn carefully from that frozen cap. Within those cores, tiny bubbles of ancient air hold the story of the atmosphere over the last several 100,000 years. They show glacial cycles, natural swings of greenhouse gases, and the delicate breathing of a planet moving through its own rhythms. As drilling goes deeper, however, the ice thins and gives way to older layers resting directly on rock and sediment. In these imagined deeper samples, taken from near the bed of the ice sheet, traces of a very different Antarctica appear. Grains of pollen, fragments of leaves, and chemical markers of soils hint at a time when the continent was milder and richly vegetated. Between these clues, the composition of trapped gases begins to resemble not only a warm world, but a busy one. In some layers, greenhouse gases rise and remain high in a pattern that echoes industrial energy use. Other compounds, usually associated with combustion, metallurgy, or synthetic chemistry, appear in combinations that seem far from purely natural. Taken together, they sketch a quiet outline of a continent that once supported forests, rivers, and organized activity on a large scale. The ice above becomes less a simple archive of climate, and more like a transparent lid placed gently over a buried center of civilization, far below the surface. Thick ice scatters and reflects radio waves in ways that can be measured from aircraft and satellites. When these signals are processed, they reveal the shape of the bedrock, hidden lakes, and long, smooth valleys beneath the frozen cover. In some stretches, the returning echoes form patterns of straight lines, regular angles, and grids that resist easy geological explanation. Features extend for hundreds of kilometers, showing symmetry and repetition that look less like carved stone and more like designed layout. In our imagination, these signals trace the outlines of silent cities and vast industrial complexes, preserved in darkness. Networks of linear reflections resemble transport corridors, conduits, or channels meant to distribute energy or materials with great efficiency. At intersections, clusters of geometric forms could have marked hubs where many systems converged, like hearts within a mechanical body. The ice does not reveal materials or colors, only the shape of what lies below, softened by time, yet still recognizably ordered. Alongside these structures, traces of life linger in sediments drawn from beneath the ice and from subglacial lakes. Within the preserved organic material, fragments of DNA hint at organisms that do not match any known modern species. Their genetic codes, in this scenario, carry patterns associated with extreme cold tolerance, resistance to radiation, and unusual metabolic flexibility. Some appear suited to processing synthetic compounds, extracting energy or nutrients from chemicals that ordinary life would find toxic or inert. From these fragments, a picture slowly forms of ecosystems not merely adapted to harsh conditions, but tuned to serve within an industrial world. We can almost see plant-like forms that tolerate dim light, nourished by warmth from below rather than sunlight from above. Microbial communities might circulate through pipes and chambers, cleaning waste streams or concentrating rare elements with quiet, tireless work. Life and machinery would blend at their edges, forming a continuous system where biology and technology support one another. Antarctica's bedrock holds more than fossils and microbial traces. Geological surveys suggest pockets rich in rare earth elements, metals, and other useful minerals scattered beneath the ice. In this imagined version, certain deposits show signs of having been selectively emptied or altered, as though mined and refined long ago. Nearby, patterns in the rock and shallow crust resemble channels and reservoirs designed to move heat rather than water. Here, geothermal activity becomes more than a curiosity. It becomes the foundation of a planetary energy network. Warmth rising from deep within Earth could have been tapped, guided, and distributed through a web of conduits beneath the continent. Power generated in this way would flow outward along hidden lines, feeding distant facilities without the need for visible surface grids. The frozen land would function as a quiet engine room, a central station driving systems spread across oceans and other continents. If such a network once existed, the collapse or transformation of the civilization that built it would not necessarily erase all traces. Metals could corrode, buildings could fall, and machines could break. Yet the layout of tunnels and chambers would still shape the rock. Residual heat patterns, altered mineral compositions, and zones of concentrated extraction would remain as signatures of long activity. To the ice and stones, these features would simply become part of the landscape, even as they carry the memory of a different purpose. Over time, climates change, and even powerful civilizations cannot fully escape the larger movements of a planet's orbit and interior. In the chemical structure of Antarctic ice, there are hints that glaciation may sometimes have progressed faster than orbital changes alone would predict. Certain markers suggest abrupt shifts in albedo, ocean circulation, or atmospheric composition that lean toward rapid cooling. In a gentle, speculative view, it is possible to imagine that some of these shifts were not entirely accidental. A culture capable of managing climate and energy on a global scale might eventually conceive of using ice itself as a shield or seal, by encouraging more reflection of sunlight, altering ocean behavior, or triggering feedbacks that favor snow accumulation. It could hasten glaciation. If focused over Antarctica, such processes could bury infrastructure under kilometers of ice, preserving it from weathering and casual discovery. The continent would become a vast time capsule, holding within it the physical remains and chemical traces of an earlier age. The motives for such an act could range quietly across many possibilities. Perhaps it was a controlled retreat in the face of limits or dangers that could not be otherwise resolved. Perhaps it was a way of locking away technologies considered too powerful or too easily misused by those who might follow. Whatever the reason, The outcome would be a continent both erased and preserved, absent from ordinary life, yet present in the deep record. In our imagination, we drift across the frozen surface, knowing that beneath the calm white plain, a very different story once unfolded. Radar echoes, buried DNA, altered mineral seams, and the chemistry of ancient air together suggest a layered and intricate past. Antarctica becomes less a blank corner of the map and more a quiet library, its shelves packed and then sealed under ice. As the winds move over its ridges and the auroras shimmer above, the continent continues to rest, keeping its long memory folded into cold and stone. Within every cell on Earth, long molecules of DNA curl and fold like quiet threads carrying memories of deep time. These chains do more than instruct cells how to grow or repair themselves. They also keep echoes of ancient choices and forgotten stories. When we read them carefully, we do not only see the path of evolution, but also patterns that feel like notes left in a margin. In frozen ground across the high latitudes, permafrost holds fragments of plants, animals, and microbes that lived many thousands of years ago. From this material, strands of ancient DNA can sometimes be extracted, cleaned, and carefully read base by base in modern laboratories. Most of what appears there fits into familiar branches of the tree of life, tracing back along known evolutionary lines. Amid those familiar branches, though, some sequences stand apart, as if they belong to no natural lineage we have ever mapped. These odd segments do not sit smoothly within expected patterns of mutation and inheritance. They look as though they have been assembled in deliberate blocks, with arrangements and motifs that resemble intentional design. Compared with our own genetic technologies, they seem to belong to a much more advanced toolkit, one that edits with subtle precision. The same or very similar segments appear scattered across different species and distant regions, as though part of a shared, coordinated plan. In our imagination, these strange pieces of code become handwritten notes from ancient bioengineers, tucked quietly into the genomes of many forms. They might adjust metabolism here, reinforce resilience there, or create hidden capacities that remain unused until certain conditions arrive. If such changes appeared suddenly and in many species at once, they would point toward a program that treats the entire biosphere as a canvas. Life would not simply be evolving on its own, but also being gently revised, version by version, by minds that understand its deep language. Amber adds another layer to this story, preserving small creatures as though time paused around them in golden drops of resin. Some insects from these ancient samples are so well kept that their internal structures and even fragments of their DNA can still be studied. In this quiet vision, certain specimens carry extra chromosomes, not involved in ordinary growth or reproduction, yet exquisitely organized. Within those added strands, patterns emerge that look more like compressed data than straightforward biological instructions. Long sequences repeat with the regularity of encoded constants, mirroring familiar mathematical relationships and geometric ratios. Other stretches align with maps of stars and orbital paths, as though charting the positions of distant suns and planets. Still, others resemble technical specifications encoded in a living script, detailing energies, materials, and constraints in an enduring, organic archive. The insect itself becomes a tiny living storage device, once flying through forests while quietly carrying an enormous library within its cells. If a civilization chose to store knowledge in this way, it would merge information and life into a single, resilient substrate. As long as the species endured, the data would travel with each generation, woven into the fabric of chromosomes. When individuals became trapped in resin and preserved as amber, a portion of that moving archive would be frozen in place. Millions of years later, the record could still be read by anyone able to open this layered language of genes and symbols. Far beneath the surface of the oceans, sediments accumulate slowly, grain by grain, through uncounted seasons. Within these dark layers, microbial communities persist under immense pressure and near total darkness, inhabiting a world that changes very slowly. From these sediments, sequences of DNA tell of organisms shaped for tasks beyond simple survival and reproduction. Some appear to specialize in concentrating trace metals, organizing them in ways useful for advanced materials or catalysts. Others neutralize complex toxins, transforming harmful compounds into gentler forms that fold easily back into natural cycles. Still others seem tuned to build elaborate organic molecules, ones that could serve as precursors for pharmaceuticals, polymers, or energy carriers. Together, they form a network of microscopic workers, distributed through the planet's crust, performing functions that resemble industry more than ecology. Factories and refineries blur into ecosystems and food webs, until the biosphere itself behaves like a quiet, self-maintaining production system. In this view, a civilization no longer relies solely on lifeless plants and machines to process matter and energy. Instead, it designs living agents that repair environments, extract resources, and synthesize needed substances with graceful efficiency. The whole planet becomes a coordinated assembly line, guided not by visible infrastructure, but by genomes tuned to planetary work. Even after the guiding culture fades, some of those organisms might continue their routines, leaving subtle biochemical signatures in sediments and rocks. Within the genomes of many modern species, there are regions that appear inactive under ordinary conditions. These so-called sleeping genes sit quietly, turned off or heavily suppressed, their functions not obviously connected to present environments. Occasionally, in controlled laboratory conditions, researchers manage to awaken such regions, carefully observing the traits that follow. Sometimes, the result is an unexpected increase in resilience to toxins, or an extension of healthy lifespan beyond what seems typical. At other times, subtle shifts in cognition, regeneration, or stress tolerance emerge, which do not map neatly onto known adaptive histories. The properties revealed can be extremely useful in industrial or technological contexts, yet appear excessive for the ecological niches we see today. It is as if parts of the genetic code were written for circumstances that no longer exist, or for roles not currently being played. These segments resemble commented-out functions in a vast biological program, waiting at the edge of activity. From this example, our thoughts can rest on a gentle possibility. Perhaps some of these dormant capacities were left intentionally, like hooks or interfaces for future societies to discover. A culture that had once shaped the biosphere might have anticipated later waves of intelligent life, leaving behind options rather than instructions. Those who came afterward would not receive clear messages, but they might find tools embedded within their own bodies and environments. In that sense, DNA becomes more than a record of descent. It becomes a medium for communication across eras. Ancient edits distribute abilities, memories, and hints through species that rise and fall, across continents that drift and change. When we read genomes today, we may be seeing only a fraction of what they have been asked to carry. The rest lies curled in quiet segments, blending the work of natural evolution with the faint, enduring touch of older hands. From the traces written in living cells, we move to technologies woven into stone itself, where computation and intelligence become geological, deep beneath mountains and deserts, far below roots and rivers. Stone rests in darkness for spans of time that feel endless. Within that darkness, crystals slowly grow, atom joining atom in repeating patterns that can remain stable for millions of years. Most of the time, these structures are treated simply as minerals, as resources, or as objects of quiet beauty in caves. Yet their ordered geometry offers something more, a natural lattice that can, in principle, hold, and organize information. Some crystals form intricate patterns that repeat with a complexity beyond what we usually expect from blind chemistry. Angles align in ways that quietly mirror mathematical relationships, and internal planes intersect according to precise numerical ratios. If we imagine each intersection, each ordered cluster of atoms, as a symbol, the crystal becomes a silent arrangement of encoded relationships. The solid lattice turns into a kind of mineral memory, a place where information could be written and later read without moving parts. In our imagination, we allow these mineral forms to serve as the basis of a very different kind of computing. Instead of etching circuits onto thin slices of silicon, a civilization might choose to sculpt information directly into growing crystals. Signals would travel as changes in charge, vibration, or subtle structural shifts, moving along lattice lines rather than metallic wires. Such devices could be buried deep underground, protected from erosion, weather, and most surface disturbances by the weight of rock above. Once we picture crystals as carriers of information, it becomes natural to think of them not as isolated objects, but as nodes in a network. In some regions, mineral veins extend for kilometers, weaving through rock in interconnected webs that branch and merge repeatedly. Along these paths, tiny fluctuations in electric potential, mechanical stress, or magnetic alignment can move slowly from point to point. A carefully designed lattice could use these variations as signals, passing messages through the crust in patient, deliberate patterns over long periods. Such a network might come to resemble a nervous system threaded through stone. Local disturbances, earthquakes, shifts in pressure, temperature changes, even variations in the planet's magnetic field would ripple through it. The crystal structures could sense and respond to these changes, adjusting their internal states to keep information flowing clearly. Self-repairing mechanisms at the atomic level might allow defects to be healed, preserving the integrity of the network across vast stretches of time. From this example, thoughts can drift toward the idea of an artificial intelligence that is not housed in a machine, but in the planet itself. Instead of running on rapid electronic pulses, it would operate through slow, resilient processes of mineral alignment and mechanical resonance. Its thoughts, if we can use that word gently, would unfold on geological timescales rather than human ones, evolving with the shifting crust. Such an intelligence could watch over tectonic movements, climate patterns, and the long rhythms of life, offering stability where needed. Some crystals might be dedicated less to sensing and more to preserving knowledge. Within their ordered frameworks, patterns could be arranged to hold vast amounts of compressed information in stable, repeating forms. Engineering, art, mathematics, histories, and quiet reflections could all be encoded as subtle differences in structure, orientation, or impurity placement. These mineral vaults would remain intact through cycles of burial, uplift, erosion, and transformation, as long as the lattice itself stayed coherent. In this way, deep crystal formations become libraries, scattered beneath continents and ocean floors. Their shelves are not made of wood or metal, but of planes and nodes in carefully chosen minerals. No flames, floods, or surface storms can easily reach them, even when mountains rise and fall. The cores of these structures may persist. Each crystal holds a portion of a much larger archive, fragments of a continuous record that stretches across multiple ages of civilization. When surface cultures wane or vanish, the knowledge they have placed in crystal remains quietly in place. New societies might rise without awareness of what lies under their feet, repeating discoveries and rebuilding tools from the beginning. If, eventually, they reach a level of understanding that lets them read the language of the lattice, the deeper record becomes accessible again. Old insights, stored far below the reach of ordinary change, can then re-enter the living world, guiding fresh decisions and designs. Through this slow exchange, information moves across time, not by unbroken tradition, but by being anchored in matter that outlasts memory. Stone shelters, patterns of thought, while generations come and go above, leaving only faint marks in comparison. To such a system, the surface of the planet is a changing interface, a place where new readers occasionally appear, then fade. The crystals below do not hurry, they simply keep their structures, holding what they were asked to remember. This vision turns technology into something inseparable from geology. Computers are no longer small, fragile devices on desks, but vast, enduring arrangements of mineral, pressure, and quiet energy. Artificial intelligence becomes a slow companion to the planet's own changes, attentive not over years or centuries, but over millions of seasons, and the ground beneath us, seemingly solid and silent, may in this gentle picture be carrying on a conversation too slow for us to hear, yet always continuing, high above the thin shell of air that wraps our world. Beyond the familiar paths of modern spacecraft, there are regions of space that change very slowly, almost imperceptibly, over vast stretches of time. In these high orbits, and in the gentle gravitational harbors we call Lagrange points, objects can remain for ages, circling or balancing in a kind of long, slow dance with the Earth and the Moon. These are places where the universe allows things to linger, where time stretches and the traces of distant ages can quietly endure. When we look into these regions with precise instruments, we find more than dust and rock. We find structures, orbiting in patterns that do not match natural debris, built from materials that remain stable under radiation and temperature swings that would slowly weaken almost anything we currently launch into space. Their surfaces are worn and darkened, their outlines softened by micrometeorite impact. Yet they retain a geometry, a sense of deliberate design. They behave like satellites, but they do not belong to any recorded human era. We can think of them as fossil satellites, relics that drifted above the planet long before our species named the constellations or mapped the sky. They circle in silence, following orbits that have remained nearly unchanged while continents shifted below, while ice sheets advanced and retreated, while forests rose and fell on the surface of the Earth. These objects, with their carefully chosen paths and remarkably enduring materials, seem crafted for a purpose we can no longer fully reconstruct, yet their presence feels calm rather than alarming, like forgotten markers left along an ancient celestial road. As we quietly observe these relics, we notice that some occupy those special Lagrange points, where the pull of the Earth, the Moon, and the Sun nearly balance. These are natural resting places, where a structure can stay for millions of years with only minimal disturbance. It is the kind of location we ourselves select for observatories and long-lived platforms, precisely because they are so stable. This familiar reasoning creates a gentle, almost comforting symmetry between our plans and whatever plans shaped these older constructions. In this view, space archaeology becomes a natural extension of what we already know on the ground. On Earth, we study foundations, buried walls, and forgotten tools to trace the lives of people who walked long before us. In orbit, we study trajectories, materials, and faint signatures of power and communication, searching for the remains of civilizations that may have reached into space and then faded, leaving behind only what the vacuum could protect. The same instinct guides both endeavors, to notice what endures, to read meaning in what time has spared. If a civilization ever became truly comfortable beyond its atmosphere, the most lasting trace of its presence would probably not be fragile cities or fleeting transmissions, but robust structures placed into the most stable orbits available. These objects, quietly circling far above weather and erosion, would outlast almost everything on the surface. In that sense, the fossil satellites we detect fit a pattern we would expect for any spacefaring culture, including our own. The thought settles gently. What we see above us might be a distant reflection of what we ourselves are beginning to do. A calm echo across time between different chapters of activity around the same planet. From the realm of silent orbits, our attention drifts outward, toward the airless surfaces and rocky fragments that share our path around the sun. The moon, softly lit in the night sky, becomes more than a distant lantern. Under careful mapping and subtle radar echoes, its surface reveals shapes that do not match simple craters and ridges. Beneath layers of dust, there are patterns of buried voids and geometric alignments, as if vast chambers, tunnels, and support structures once lay just below the surface, later covered by slow, steady falls of regolith. On nearby asteroids, we notice grooves and linear depressions that resemble extraction pits and transport channels more than random fractures. They form networks and repeating motifs, spreading across irregular bodies whose gravity is so gentle that even modest efforts could reshape them. Instead of seeing only rocks tumbling through space, we begin to see them as former work sites, places where material may have been gathered, processed, and quietly moved along a chain of activity threading through the inner solar system. Mars, with its wide plains and soft slopes, adds another layer to this quiet picture. High-resolution images hint at surface patterns that echo industrial zones we recognize from old landscapes on Earth, arrangements of terraces and basins, long straight alignments that trace efficient paths across the ground, subtle discolorations in the soil that line up in ways reminiscent of access routes and storage fields. The wind has blown over them for countless seasons. Dust has settled, and yet the overall organization remains visible, like the faint imprint of an earlier purpose embedded in the terrain. In this reconstruction, the solar system takes on the character of a once busy, now resting network. The moon serves as a stable platform, its surface supporting buried installations, storage caverns, and manufacturing halls shielded from radiation and micrometeorites. The asteroids provide raw material, approached carefully and reshaped, just enough to yield what was needed. Mars offers valleys, plains, and natural shelters where more extended operations could unfold under a thin sky. It is easy to picture a time when transport ships moved regularly between these places, not in frantic haste, but in steady cycles, following predictable paths like trade winds in an earlier age of oceans. If traces of such activity are truly present, they suggest that at least one civilization arising from Earth once stepped beyond dependence on a single planet. It reached a stage where its survival, its energy, and its resources were distributed among several worlds and countless rocks in space. In that state, the home planet becomes only one part of a wider web. Important, but no longer the only center. This idea is not a demand for belief, nor a puzzle to solve tonight. It simply rests there as a possible chapter in the long, slow story of life in this system. As we drift through these images in our minds, we recognize how naturally they align with our own early steps outward. We place robotic explorers on Mars, talk of mining asteroids, design habitats for the moon, and dream of moving gently among the worlds that share our star. The ancient patterns hinted at in orbital debris and surface features become a soft mirror, reflecting back to us a vision of what any interplanetary civilization might look like when viewed from far away in time. In this shared stillness, the moon continues to glow. Mars turns slowly under its thin atmosphere, and the asteroids trace their quiet paths in the dark. Around and between them, the memory of past activity and the possibility of future journeys blend into one continuous, unhurried scene, extending outward into the wider galaxy that waits beyond. Calm and patient, with its own stories held in reserve, far below the restless skin of the waves. There is a level of Earth where almost nothing happens quickly. The light from the sun never reaches this place. The winds never stir it, and storms that shake the surface cannot touch it. Here, on the floor of the deep ocean basins, pressure is immense, darkness is complete, and change comes so slowly that millions of years pass like a single, unbroken night. In this quiet environment, the rocks and sediments form broad plains and gentle slopes, stretching farther than our eyes could ever follow. There are no crashing breakers here, no shifting dunes of sand blown by the wind, no rain carving valleys and cliffs. The deep floor of the ocean is wrapped in a kind of stillness, where currents move like slow thoughts and the world above feels very far away. If we picture a structure resting here, a wall or a tower, or the outline of a city, we begin to sense why this realm is such an effective archive. On land, mountains crumble under the patient work of ice and rain. Rivers cut valleys, and entire coastlines retreat and advance over long ages. Continents drift, glaciers advance and melt, and everything exposed to the air is constantly being worn down, buried, lifted, and reshaped. By contrast, a structure settled gently onto the floor of a deep trench or an abyssal plain would be surrounded by water that hardly stirs, protected from storms, safe from the rapid rhythm of seasons. A thin rain of microscopic particles would fall softly from above, year after year, forming a blanket of sediment that covers and preserves. Over spans of time longer than any human history, this slow snowfall of dust from the upper ocean could seal entire landscapes in a dark, protective layer. When we think about where traces of an ancient technological culture could remain most intact, our usual instinct points us toward deserts, ruined temples, and forgotten cities on land. Yet our planet is mostly ocean, and the deep basins of that ocean are places where change proceeds at a very gentle pace. If a civilization had ever wished to leave behind structures meant to endure almost indefinitely, the deep seabed would be a remarkably suitable choice. This idea offers a calm explanation for why traditional archaeology, focused mainly on dry land, might find so little of a very old technological past. The most enduring remnants would not be standing on hillsides or buried under cities. They would be resting in the long, silent night beneath the sea, out of reach of ordinary tools and methods, waiting in a realm that our species has only just begun to systematically explore. As we drift with this thought, our attention follows the beams of instruments that quietly scan the depths. Instead of our own eyes, we rely on waves of sound that travel through the water, touch the seabed, and return. These echoes are turned into delicate maps, pale outlines of the hidden landscape below. On some of these maps, long, straight features appear, crossing the darkness in lines that seem too regular to be chance. Broad, level platforms rise gently from the surrounding plain. Grids and repeating angles sketch patterns that, at a glance, resemble foundations and roads. Whether natural or not, they lend themselves to a particular kind of imagination, one that moves slowly and without urgency. In this vision, the ocean floor becomes host to vast, submerged cities. We can picture wide avenues laid out with quiet precision, stretching from one horizon to another. These would not be streets filled with sunlight and air, but corridors suspended within pressure-resistant shells, where life continues in a carefully controlled environment while the water outside stays cold and dark. Along these imagined avenues, we find nodes that function as stations and junctions, places where vehicles might dock, where resources from the surrounding sea are drawn in and transformed. The energy that powers these systems could come from the deep itself, from the gentle tug of tides, from slow currents, and from the steady warmth of hydrothermal vents, where the planet's interior sends heat upward in narrow, glowing plumes. A civilization living here would not fear storms or drought. Its power lines would be anchored in the constant processes of Earth's interior and oceans. The network beneath the sea would connect processing centers that filter minerals from seawater, capture dissolved gases, and harvest heat. In this picture, the ocean is not an obstacle but a shield, wrapping these submerged structures in a constant, protective embrace. The surface world might face impacts from space, shifting climates, or long winters of volcanic dust, while deep below, the temperature changes only by small degrees, and the pressure, though great, remains dependable and steady. If such a civilization existed, its living space would not be limited to continents and islands. There would be layers of habitation, cities on land, habitats in orbit, perhaps outposts on other worlds. And beneath all of that, these slow, secure superstructures on the ocean floor, our planet would become a nested arrangement of environments, each adapted to a different rhythm. From the rapid cycle of day and night at the surface to the almost timeless quiet of the abyss, as we let this layered image settle in our minds, Earth appears not just as a blue sphere in space, but as a world with hidden tiers of possibility. Above, clouds drift and continents move through the ages. Far below, there may be patterns on the seabed that hint at deliberate design, or simply at the subtle order of geology. In either case, the deep remains a calm, concealed stage, a place where time stretches out and structures, whether natural or imagined, can rest for ages in the gentle darkness of the sea. There is a quiet impulse that seems to live in every thinking species, a soft instinct that appears when we lift our gaze beyond our own lifetime, the wish to leave something behind for those who will follow. Not just monuments or ruins, but messages, hints, pieces of understanding that might help another generation, or even another civilization, move a little more safely through the unknown. In the stillness of deep time, this impulse becomes a kind of system, a diffuse network of memory and warning, scattered across matter itself. We can picture it as a calm, silent library, not built from paper and ink, but from crystal, mineral, and air. In this imagined library, each civilization that reaches a certain point of awareness leaves behind carefully designed traces, not in words we could speak aloud, but in patterns that can endure when languages have faded and surfaces have crumbled. The shelves of this library are made of atomic lattices and frozen ratios, of gases sealed away in stone. Some messages rest in the perfect geometry of crystals, where the regular arrangement of atoms can be subtly altered to hold patterns, like a slow, patient code carved into the structure of matter. Others are hidden in the proportions of different isotopes within minerals, tiny variations in the weight of atoms that tell a story about what once happened on a planet's surface, about heat and radiation and the chemistry of ancient oceans and skies. Still, others drift within ancient pockets of atmosphere trapped in ice or rock, preserving a faint, fragile record of how a world once breathed. All of these forms can be imagined as pages in that insurance library. They are designed not for speed, but for endurance, meant to survive floods and fires, erosion and tectonic movement, so that somewhere, far ahead, curious minds might still find them. As we move slowly through this picture, we begin to sense that the ones who came before us, whether they were human ancestors or some earlier, forgotten civilization in this speculative landscape, understood that worlds are fragile, and that intelligence can be both a gift and a risk. These messages, scattered through crystal structures, isotope ratios, and ancient gases, become gentle evidence that those who preceded us had already glimpsed the possibility of collapse. They might have known, in their own way, that technology can grow faster than wisdom, that climates can shift beyond what life is prepared for, that power can outrun restraint. In response, they chose not only to live their own moment, but to write quietly into the fabric of their planet, hoping that someone, someday, would read and understand enough to avoid repeating the same mistakes. From here, our wandering attention begins to drift toward the content of these imagined messages. If we could slowly decode them, if we could translate patterns into meaning, we might find that they speak about more than dates and measurements. They might unfold as a kind of survival guide for any civilization that reaches a dangerous threshold of knowledge. We can picture instructions about energy, offered not as strict rules, but as calm suggestions anchored in experience, ways of drawing power from a star or a planet's interior without poisoning the air or overheating the climate. There might be descriptions of how certain choices warmed their world too quickly, how ice retreated and storms changed, and how gentler methods, discovered later, brought a new balance. In the same layered code, we might sense warnings about weapons that could end a species in an instant, about tools that split atoms or alter living cells with unsettling ease. Perhaps there are passages that touch on the creation of self-modifying technologies, systems that can learn and adapt on their own, moving in directions their makers did not fully anticipate. The message then would not be to fear such abilities, but to approach them with a steady, patient awareness, remembering that power without reflection becomes unstable over long stretches of time. Alongside these cautions, we can imagine that the messages also carry examples of what worked, methods for cooperation instead of conquest, ways of organizing societies that reduced the chances of catastrophic conflict, techniques for restoring damaged environments so that life could continue. In this way, the library in crystal and stone ceases to feel like a list of threats, and instead begins to resemble a handbook, compiled across many cycles, shaped by hard-earned lessons. It hints that the rise and fall of civilizations may happen more than once, not in complete darkness, but with threads of memory stretching across the ages. Each layer of rock, each trace of altered isotope, becomes a quiet voice saying, "We have been here before. We have faced something like this, and we left what we could for you." As we rest with this idea, a gentle awareness forms between us and those imagined predecessors. The story we are following is no longer only a search for evidence. It softens into a kind of dialogue across deep time, a conversation carried by minerals and ancient air. Our place in this conversation is not defined by urgency, but by a calm recognition that we are part of a much longer sequence of attempts, failures, and renewed beginnings. In the background of this unfolding, an ethical question arises, not demanding an answer, simply hovering like a distant star, surrounded by these careful warnings and quiet gifts. How might we choose to walk through our own moment in history? The reply does not need to come now, and it does not need to be complete. It can grow gradually, as we linger with the thought of crystals, isotopes, and ancient skies, and as we continue to drift, calmly, with all those who came before and all those who may one day read what we leave behind. We drift now into the idea of long, slow cycles, in which civilizations rise, flourish for a while, and then gently fade, leaving only quiet traces in the fabric of a planet. On human scales, a century can feel vast. Yet, on the stage of cosmic time, cultures might appear and disappear over stretches of tens of thousands of years, like waves slowly rolling in and out along a shore that never tires. Each civilization lives through its season, reaches a certain brightness, and then gives way, while the planet quietly keeps its memory in stone, in ice, and in invisible patterns written into its air and oceans. When we imagine these cycles, we can picture them not as straight lines with a clear beginning and end, but as spirals that turn again and again, At first, there is discovery and curiosity, a gradual unfolding of tools and technology. And then, over many generations, an acceleration. As knowledge builds upon knowledge, the spiral tightens as energy use grows and reach extends farther into the environment, perhaps into space, perhaps into the deep interior of the planet. Eventually, the spiral approaches a threshold where the same power that allowed growth also becomes fragile, making the whole system sensitive to small disturbances, to small mistakes that echo through the network of life and machines. Collapse is not a sudden, dramatic event, but a long unwinding. Infrastructure is slowly abandoned. Great projects are left incomplete. And over thousands of years, the visible structures wear down. What remains are subtle signatures, unusual patterns in buried layers of rock, traces of altered climates recorded in ancient ice, strange combinations of materials that do not occur naturally, and perhaps a few resilient constructions that resist erosion and time. These become soft fingerprints of a culture that once reshaped its world and then passed away, joining many others in the planet's deep archive. If such patterns repeat not just once, but many times across millions of years, the picture becomes one of recurring cycles, civilizations rising, reaching a technological intensity, and then dissolving back into the background. In that case, the quiet challenge for any advanced society is not simply to build more or reach farther, but to gently find a way to step out of the spiral of self-destruction. The goal is no longer only progress, but learning how to remain, how to soften the peaks and valleys, and how to coexist with the planet without triggering the fragile point where everything becomes too unstable to endure. From here, we can let our attention move toward another layer of this imagined history, the possibility that some ancient culture, having lived through its own cycles of rise and collapse, chose to leave behind more than just ruins and isotopic traces. In this vision, they seeded the planet with systems designed to watch and to protect, to guide the planet through dangerous transitions the way a gentle guardian might watch over a sleeping child. We can imagine Earth wrapped in a faint, intricate network, woven from crystalline structures, tuned magnetic fields, and delicate instruments buried deep under rock or hidden in the ocean floor. These devices would not need to be loud or obvious. They would sense subtle shifts in pressure and heat, in the movement of tectonic plates, in the circulation of the atmosphere and the oceans. When a disturbance grew too strong, when a volcanic chain threatened to release too much energy at once, or when currents shifted in a way that could destabilize climate, tiny corrections would be applied, spreading out gently over long spans of time. In this picture, the planet has been given something like an artificial immune system, built not from cells and proteins, but from fields and materials, algorithms and feedback loops. Just as a biological immune system responds quietly to threats long before we feel sick, this planetary system would adjust and recalibrate, smoothing out extremes and keeping conditions within ranges that remain friendly to complex life. To those living on the surface, such a guardian network would be invisible. Seasons would come and go, ice ages would wax and wane, and it might simply seem that Earth is unusually stable, unusually generous in sustaining life over astonishing periods. Seen this way, the seeming luck of our planet's long habitability might be more than chance. It might be, in this gentle speculative story, the legacy of beings who once faced their own crises and decided to build a scaffolding to protect what came after them. As we drift through these thoughts, we can picture ourselves as latecomers who have inherited a world that is quietly supervised by systems we do not yet fully understand. At some distant point, humanity might learn to read and interpret these subtle networks, to work with them, or to gradually replace them with new layers of guardianship, becoming conscious participants in a story that began long before our recorded history and will continue long after our present moment has passed. From the idea of planetary guardians, our thoughts can expand toward a different kind of legacy: the traces of consciousness itself. If a civilization learns to shape matter on planetary scales, it may also learn to gently record the delicate patterns of thought and memory that live in its minds. Instead of allowing awareness to vanish with each passing generation, such a culture might find ways to imprint its mental patterns into durable substrates, preserving something of its inner life long after bodies and cities have faded. One of the easiest images to hold is that of crystals, growing slowly in the dark, their internal structures ordered and precise. We can imagine technologies that use these ordered lattices as canvases for information, encoding not just simple signals, but the flowing patterns of neural activity that once moved through living brains. Over time, as methods become more refined, the information might be stored not only in solid matter, but also in subtle quantum fields that extend through and around the material, forming a gentle cloud of encoded states that carry the echoes of thoughts, memories, preferences, and ways of seeing the world. If this process is repeated for many individuals, a new kind of society could emerge, one that no longer depends on biology. Instead of neighborhoods formed by streets and buildings, there would be neighborhoods of patterns within the same crystalline and field structure. We might picture vast cities of consciousness, where each pattern is a presence, a continuing awareness, able to interact with others through shared networks of information. These cities would not need sunlight or food, only stable conditions and a steady flow of energy to maintain their subtle dynamics. Within such a society, time would feel very different. Without the urgency of aging bodies, processes of thought could stretch out, becoming slower and more expansive, or faster and more intricate, depending on the chosen mode, over spans that would cover the rise and fall of many physical civilizations. These stored consciousness communities could continue to reflect, to simulate, and to explore possibilities in a safe interior space of computation and shared imagination. They might quietly study the physical universe, model future scenarios, and decide, with great care, when and how to touch the material world again. In this contemplative vision, a civilization does not truly end when its physical infrastructure decays. It changes phase, passing from a biological form into an informational one, from muscles and hands into patterns and fields. The story of that culture continues in these gentle cities of awareness, which might occasionally influence the outer world. They could send signals, guide younger civilizations with subtle hints, or maintain the planetary guardian systems that stabilize climates and tectonics. In doing so, they would become part of a larger tapestry that links matter, life, and mind across immense stretches of space and time. As we rest with this idea, our own planet as one node in a much wider network, somewhere in deep time, other worlds may have made similar transitions, leaving behind both material guardians and communities of stored consciousness, all drifting together in the quiet background of the cosmos. The universe, in this soft picture, becomes not just a collection of stars and planets, but also a gentle archive of experiences, carefully preserved and slowly evolving, while we, for a little while, listen, breathe, and float along its unhurried currents. Around us, the galaxy stretches out like a vast, dim tapestry, and within this quiet expanse, our small world comes to a gentle branching in its path, the story we have been drifting through of ancient guardians, stored consciousness, and recurring cycles of rise and collapse, now settles softly on the present moment, where Earth turns slowly through space, carrying a young civilization that is beginning to sense its place in something larger than itself. We can picture our planet as one luminous point in a wider web, a node in a network that might span the spiral arms of the Milky Way. In the faint records of starlight, Astronomers sometimes notice stars whose brightness dips in ways that are hard to explain, with simple shadows of planets. And here, the imagination moves toward the possibility of great engineered shells or swarms, built to harvest energy from their suns, in the irregular patterns of cosmic rays. Some models allow us to wonder whether a fraction of this invisible rain has been gently shaped or modulated, like a quiet signal riding on top of a natural background. Across the distances between stars, we can imagine beams of radio, light, and particles forming a delicate lattice of communication. A galactic conversation unfolding so slowly and so faintly that, from the inside of one young world, it feels almost like silence. Within this soft picture, Earth is not isolated, but part of a much older story. There may have been times, long before our written history, when our planet was more deeply involved in this imagined galactic community, contributing signals of its own, receiving guidance, and participating in shared projects that we now only glimpse in myths and geological hints. We can let the image form of Earth as a regional center, a kind of crossroads where information, technology, and living beings once flowed in and out, leaving behind the guardian systems and stored consciousness we have quietly considered. If this is so, then our current civilization would be something like a new layer on an old node, a fresh pattern forming over a well-used point in the network. We might not be the first intelligence to bloom here, but we may be among the first, with the chance to see the full outline of the spiral we are moving along. That realization gently shifts the meaning of our present era. It becomes not only a time of growth, but also a moment when we can sense the possibility of stepping away from the familiar loop of acceleration and collapse, and instead easing into a more stable rhythm that could one day reconnect with that wider cosmic web. As our thoughts settle on the present, the scale changes from millions of years to something far shorter, almost like zooming from a galactic map down to the soft glow of city lights on a single rotating globe. The changes shaping our world, now the rapid expansion of technology, the strain on ecosystems, the growing ability to alter climate, and even the inner structure of matter are unfolding not over vast epochs, but over spans of time that fit within a human lifetime, or a few generations. On the scale of the cosmos, this is just a brief flicker, a narrow window in which many trajectories converge and begin to diverge. It can be helpful to imagine this moment as a long curve in a quiet mountain road. The vehicle has been gathering speed for some time, coasting downhill, the scenery passing faster and faster outside the windows. Up ahead, the path bends, not with a sudden drop, but with a gentle turn that leads either toward a safer, more level stretch or toward rougher terrain where the ride becomes unstable. Along the edges of this road, we can imagine signs that have been placed by hands long vanished, messages written into ice cores, into layers of sediment, into the composition of the atmosphere, and perhaps into crystalline networks still humming faintly below our feet. Each of these signs carries the same calm reminder. Many others have traveled this way, and their stories are quietly present in the world itself. In this light, all the clues we have touched, the traces of past cycles, the possibility of guardian systems, the idea of stored consciousness and distant networks fold together into a single, gentle awareness. Our species moves through a brief period in which its choices about energy, technology, and relationship with the planet have far-reaching effects. Yet this realization does not need to be frightening. It can be felt simply as a soft understanding that our actions ripple outward, touching not only our own future, but also the long continuity of life that came before us and may come after us. If earlier civilizations on Earth and elsewhere reached similar turning points, some may have tightened the spiral until it broke, becoming only a thin layer in the geological record and a faint whisper in the galactic background. Others, perhaps fewer, may have found ways to slow down, to align themselves with their worlds in a more gentle equilibrium, and in doing so, to remain present long enough to join or rejoin that imagined community among the stars. We find ourselves, now, in a moment that resembles those earlier forks, aware enough to sense the patterns, yet still early in our understanding of what a different trajectory might look like. The question of which path humanity will follow drifts quietly above us, like a distant constellation that we can notice without needing to trace every line between the stars. It does not demand an immediate answer, nor does it press on the mind. It simply hovers there as a soft backdrop to our days and nights. As Earth continues its slow journey around the Sun, and the Sun circles the center of the galaxy, we can picture our world as a small, luminous node in a vast, tranquil network, carrying within it the memory of what has been and the possibility of what might yet unfold. While we rest, breathe, and let our thoughts move as gently as the turning of the sky, when we step back and look at the entire picture, what remains is not a claim that ancient civilizations definitely existed before us, but something more subtle, an understanding that Earth remembers in ways very different from humans. It does not preserve names, faces, or narratives. Instead, it holds on to traces of energy, chemistry, and transformations powerful enough to be etched into time itself. Layers of rock, ice cores, microscopic metallic dust, and unusual isotope ratios do not give us certainty, but they open a wide space for reflection, a space where imagination and science can coexist without the need for rushed conclusions. Within that space, humanity no longer stands as the single central figure, but as one part of a long sequence of possibilities that may have unfolded, or may yet unfold, on this planet. Thank you for accompanying us on this quiet journey. And if you are willing, we will continue drifting together slowly to explore more surprises, more mysteries, and more unanswered questions in the vast, patient universe unfolding gently before sleep.